The Incremental Snapshot engine is a subsystem responsible for managing point-in-time captures of application state across distributed nodes. The engine maintains version snapshots at configurable intervals and provides consistent read access to historical state representations. The primary function is invoked through the snapshot create method, which accepts a state identifier and an optional retention policy parameter. All snapshots are immutable after creation and stored in the configured snapshot backend. Snapshot versioning operates on a monotonically increasing sequence number assigned at creation time. Each snapshot record contains a version identifier, creation timestamp in UTC, state hash, and a pointer to the underlying data block. The version sequence begins at 0 and increments by 1 for each successful snapshot write. Version numbers are never reused and persist for the lifetime of the snapshot repository. Gaps in the sequence indicate failed or aborted snapshot operations. The snapshot retention policy defines the lifecycle of stored snapshots and governs automatic pruning. 3 retention modes are available: unlimited, time-based, and count-based. Unlimited mode retains all snapshots indefinitely. Time-based retention deletes snapshots older than the specified duration in seconds. Count-based retention maintains a maximum snapshot count, removing oldest versions when the limit is exceeded. The default mode is time-based with a retention window of 30 days. Snapshot creation is an atomic operation that ensures consistency of the captured state. The engine first acquires a read lock on the application state, computes a cryptographic hash of all state components, and writes the snapshot record to the backend store. If any step fails, the entire operation rolls back and no partial snapshot is persisted. The entire process is logged in the audit trail with transaction identifiers for traceability. Concurrent snapshot requests are serialized through an internal lock. The snapshot backend interface defines 3 mandatory operations: write, read, and delete. The write operation accepts a snapshot record and returns a storage location identifier. The read operation retrieves a snapshot by version number and returns the full state data block. The delete operation removes a snapshot record and its associated storage. All backend implementations must provide these operations with at least once delivery semantics and support concurrent access from multiple client threads. State hash computation uses SHA-256 hashing apply to a canonical representation of the application state. The canonical form is generated by serializing all state components in a fixed order defined by the state schema. Nested objects are serialized recursively using the same canonical ordering. The resulting hash is a 64-character hexadecimal string that serves as a cryptographic fingerprint of the snapshot. 2 snapshots with identical hashes are guaranteed to contain identical state data. Incremental snapshots reduce storage overhead by capturing only state changes since the previous snapshot. The engine maintains a delta log tracking all state modifications between snapshots. When creating an incremental snapshot, only the delta log is stored rather than the full state. Delta snapshots contain a parent version reference pointing to the previous snapshot, from which changes are computed. Full snapshots are automatically generated at configurable intervals to maintain consistency and prevent deep delta chains. The snapshot read method retrieves a snapshot by version number and reconstructs the full application state. If the requested version is an incremental snapshot, the engine recursively reads parent snapshots and applies delta logs in sequence to reconstruct the state at the target version. This process is transparent to the caller. Read operations may be executed concurrently with snapshot creation operations without blocking. The return state object is immutable and reflects the state at the exact moment of snapshot creation. Snapshot consistency verification is performed periodically through an internal validation process. The engine recomputes hashes for all snapshots and compares them against stored values. If a discrepancy is detected, the snapshot is marked as corrupted and an alert is generated. Corrupted snapshots are not removed automatically and must be handled through operator intervention. The validation process runs in the background and does not block normal snapshot operations. Validation frequency is configurable and defaults to once per hour. The snapshot metadata index is maintained in memory for fast lookups of snapshot properties without reading the full backend. The index contains version numbers, timestamps, state hashes, and size information. The index is rebuilt from the backend at startup and kept consistent through log-based replication. Index entries are accessed through a lock-free concurrent hash table implementation. The total memory overhead for the index is proportional to the number of retained snapshots and typically represents less than 1% of total heap allocation. Pruning of expired snapshots is controlled by the configured retention policy and executed by a background maintenance process. The pruning operation scans the snapshot metadata index and identifies candidates for deletion based on creation timestamp or retention count. Identified snapshots are deleted in reverse version order to maintain consistency. During pruning, snapshots remain readable and the metadata index is updated atomically. The pruning process generates audit logs for each deletion operation identifying the version and reason for removal. Error handling in snapshot operations follows a consistent pattern of immediate failure with detailed error codes and context. Operations that fail due to backend unavailability return a temporary unavailable error code and may be retried. Operations that fail due to corrupted data return a data integrity error and require manual intervention. Operations that fail due to invalid parameters return a validation error with specific field information. All errors include timestamps and are logged to the diagnostic event stream for troubleshooting purposes. Snapshot replication ensures high availability across distributed deployment clusters. Each snapshot created is automatically replicated to configured replica backends asynchronously. Replication uses a log-based protocol where snapshot creation events are appended to a replication log and consumed by replica nodes. Replica nodes apply snapshots in order and maintain identical snapshot repositories. Replication lag is measured in seconds and monitored continuously. Replication failures are retried with exponential backoff up to a configurable maximum retry count. Configuration parameters for the snapshot engine are specified in the engine configuration structure. The snapshot interval parameter defines the interval in seconds between automatic full snapshots and defaults to 3600 seconds. The incremental enabled flag controls whether delta snapshots are used and defaults to true. The retention policy parameter specifies the retention mode and duration. The backend type parameter selects the snapshot storage backend. All parameters are immutable after engine initialization and cannot be changed at runtime. Monitoring and observability of snapshot operations are provided through metric export and event logging. Standard metrics include snapshot creation count, snapshot creation latency (MS), and snapshot retention count. Event logs record all snapshot operations with full context including version, timestamp, and operation status. Health check endpoints expose snapshot engine status including the most recent snapshot version and time since last snapshot. Metrics are exported in the standard Open Metrics format compatible with standard monitoring systems. Recovery from snapshot engine failures follows a defined initialization protocol. On startup, the engine loads the snapshot metadata index from the backend. If the index is corrupted, the engine rebuilds it by scanning all snapshot records in the backend sequentially. Once the index is loaded, the engine verifies the most recent snapshot for consistency. If verification fails, the engine falls back to the previous snapshot and reports an alert. Full operational readiness is achieved when the metadata index is loaded and validated successfully.